Hi, everyone. Welcome to Riot's Lunch and Learn series, the place where we feature all of Riot's sponsors. My name is Caroline Griffin. I'm Riot's Director of Operations, and I'm super excited to have Ubidots CEO and co-founder with us today to talk about predictive maintenance techniques for non-data scientists. Ubidots has been a longtime supporter of Riot, and we are very thrilled to have Augustin here with us today. Just a couple of quick reminders before we get started. This session is being recorded and will be posted to Riot's YouTube channel and then posted to the meetup group where you found it. And then the last reminder is that if you have any questions throughout the presentation, please do put those in the chat box and we will make sure to get to all of those if we have time. But without further ado, thank you for being with us, and I'll hand it over to Augustin. Thanks for being with us, Augustin.
Caroline, thank you very much, and thank you all for being here. So today, as Caroline said, I'll be sharing some of my journey as the CEO, but also the product guy, or one of the product guys behind the curtain at Ubidots, when asked about predictive maintenance. As you know, as you can imagine, some of our clients have begun to create some type of optimized maintenance program. So this is today really about that journey, just sharing, what I encountered, how we have tackled this type of challenges, most importantly, as a non-data scientist myself. So for those of you who might not be familiar with Ubidots, we are a drag and drop IoT development platform. We empower thousands of IoT engineers, IoT entrepreneurs, system integrators, and even some enterprises to create entire IoT projects without the need to hire a software development team. So in Ubidots, you will find most backend and frontend components that you need to succeed at your IoT initiatives. Today we'll be switching between the presentation and my Ubidots screen so that you can see like a hands-on approach of these techniques we'll be talking about. So first of all, I will be talking about how IoT is kind of in the middle between preventive and predictive. It's kind of that enabler that's sparking the conversation in a lot of places about predictive maintenance. And then the fun part, which will be 4 specific ways that we can use to create optimized maintenance programs for either yourselves, if you are working at a manufacturing site or an end user, or for your clients in the case that you are a system integrator or an IoT entrepreneur. So first of all, the fundamental question in predictive maintenance or in maintenance in general is to service or not to service. So usually a maintenance engineer will face 3 different paths when it comes to maintenance. The first one is maybe you are maintaining the machine too frequently, which is okay from the preventive point of view. However, it will also represent some costs, labor costs of whoever is doing the maintenance, travel costs in the case where the machines are spread out across the region or even inside the same city, and then the spare parts that you need to replace whatever you're servicing. The second path is not maintaining a machine frequently enough, which is the most undesired path, of course, because it usually lead to costly repairs, lost production. Imagine a factory that's producing X amount of units per minute or per day, or even an oil rig, for example. Any downtime, any minute or any hour where a machine or a process is not flowing because there's a bottleneck in a failure in a machine, it will lead to lost production, therefore lost money at the end. And also there could be some legal and medical liabilities depending on how hard or how unexpected this downtime could be. It could create a liability that also translates into unsafe work environments and also monetary costs, of course. And then the third path is the desired one, which is maintain exactly when needed. It is a predictable cost. It's not a cost that you can eliminate, but it's at least expected. So in order to provide as an intro, like a sense of why this topic has become so important in the last few years, I went through a lot of research in well, Google and all the sources, trying to find like real examples of how much this could cost usually a manufacturing plant or a company. I found this sample data. It is still fictitious, but the source comes from someone who has a lot of experience out in the fields. So it was the most trustworthy one I could find, and also closest to reality based on our own observations. So imagine that this company has close to 400 machines and has been recording the failures and services throughout 2 years. And each, in the case of unnecessary maintenance, there were only 9 incidents. Each one cost close to $1,000, and that would be the total cost. The desired one, which is the timely maintenance, this cost cannot be eliminated. You still need to do it. And then the repairs due to unexpected failure or lack of maintenance could go as high as 380 and cost this cost per incident, it could be close to $12 million. So imagine if we could create an optimized maintenance program to reduce 50% of unneeded, unreactive maintenance, we will be saving this factory or this company close to $6 million over the course of 2 years. Now, you might be thinking, well, if this is preventive and the other one is predictive, then why not doing predictive alone? Clearly, there's, at least in this case, a lot of value to be generated. Well, that's also our initial thinking a few years back when we started tinkering with this machine learning and all the tools that are out there. And to be honest, it was quite overwhelming. So I think that this is, I will be showing you kind of the ecosystem, the way I understand it. So again, I'm not a data scientist. I might be wrong here at some categorizations being made, but this is what an IoT engineer will face when confronting a predictive analysis problem. So first of all, there needs to be data. And this is, we haven't even gotten to data science, and it is a very hard part, because imagine that this factory, maybe they didn't record every failure in a categorized manner or a database. So sometimes they don't even have IoT devices. Their PLCs are not instrumenting the data already. So even if somebody had the budget and the will to do predictive maintenance, if they don't have years or at least months of historical data, both like good observations and failure observations, there won't be enough meat, there won't be enough to work with in order to train a model. So that's kind of the first challenge. But again, we could say that's still within our domain as IoT engineers. When things begin to get more complicated is when you get into data science. So this is a process of taking that data, doing some changes that we will see in a minute, well, at the end, picking a model to train that data, and then testing the model against an accuracy score to see if it's good enough to predict new observations. Something I learned in this process is that data science is like an empirical science. Sometimes I'm an electrical engineer by background, and we tend to think that, for example, when we code an IoT device on how to send data to a cloud, it's a very deterministic thing to do. So you would find a tutorial, you would read a few sources, and then you will be able to flash a firmware and just achieve your objective of programming a device or sending data to Ubidots. Data science is empirical, which means it needs some experience. It benefits from experience. It benefits from understanding the predictive problem you're facing. And most importantly, it benefits from iterations. So the more you iterate along this process, the more accurate model you're going to get. So to get a sense of that ecosystem, all the way from available programming languages to note-taking tools to test those models, libraries in Python, in this case, to manipulate data, not exactly machine learning, and then the machine learning libraries that are out there. I'm sure there are more, by the way. This is just like an initial research that I did. And then to make things more complicated, you got something called deep learning, which is something like Google TensorFlow, Keras, PyTorch, which are used when for more advanced computations like image analysis, etc. So even after you have figured out the model that you want to use, then there's a very important step that makes it all worth, which is the deployment, also called ML Ops. It is the process of actually deploying this so that the other applications can read your predictions, can read your model, can make use of it through an API. So there are a lot of tools that I found in this while preparing for this webinar. To my surprise, I couldn't find like something friendly enough for me to just send, I don't know, 10 sensor variables and then get a prediction based on a model that I could upload. So if you find it, or if you know about one, please let me know. There was something like RapidMiner Go, but it was shut down last month. And now they only sell enterprise licenses for $100K per year. So all of this to make a point that it is an ecosystem that's moving a lot. So it's worth definitely being updated about it to see what type of tools you can use for your own application. And at the end of in the final exercise, we will see how we have managed to simplify this to a point where it can be used at least within time series /IoT /predictive maintenance applications. So we're here today to argue that this line that divides predictive and preventive doesn't have to be like a very well-defined line. Like there's a lot of shades in the middle. And if you look at the definitions, there is like a fundamental difference between preventive and predictive, which is condition monitoring. This appears in manufacturing literature dating back to the 70s and the 80s. Condition monitoring was the process of taking notes about the state of a machine and its environment, and then logging it either manually, offline, in a local notebook or file to understand what was going on with the machine. Now, the condition monitoring today, thanks to IoT, has become online. So we went from offline to online condition monitoring, not only of the machine, but also the process variable, so the amount of units produced, the stop times, the quality, also the energy that's being used, and even environmental variables around the workplace that could affect the productivity of a worker, of the productivity of the machine. So this is really IoT, if you look at the definition. So the good news about today's environment is that we can leverage a lot of IoT technologies to do something that is between preventive and predictive. So I wouldn't say it's just preventive, because it does have a component of online monitoring, proactive maintenance, as we will see in the examples, but also a predictive component or better said, it is the fundament that will later feed the models that we will need to train in a predictive approach. So without further ado, let's get hands-on. Let's start with some real world examples that we have been observing, within our own experience with clients. Please, by the way, if you have any questions during these exercises, feel free to raise your hand or to just simply drop a question in the chat. That way, we can make it more interactive and we don't have to wait until the end for the questions. So the first technique is the usage-based maintenance. So imagine that there's a factory with 100 machines, each one being serviced every 2 months. So if you look at a particular machine, these bars would mean the service moments. In terms of costs, if you multiply 6 visits, each visit being $500 times 100, we will be looking at $300,000 in maintenance costs. But this is like doing the homework. This is like reading the manufacturer guidelines, and just doing it regardless of whether the machine was used or not. So a better approach will be to log the runtime in a system that it's monitored in real time in order to service the machine exactly when needed based on the runtime alone. The cool thing about this is that it is like a low-hanging fruit in a lot of industry 4.0 use cases that we observe. It's typically how they begin getting the foot into the door to start talking to customers, because in this example, there will be savings of $100K per year, for example. And from a system point of view, it's a very simple device. Like literally what you need is just one or zero, like on or off, which could be accomplished by a current sensor that is attached to the power line of the machine. If it has current, then it's a 1. If it doesn't have current, it's a 0. It could be a vibration sensor that, if it's vibrating, it's working. If not, it's offline. And that way you can start having like a runtime figure or an hourly usage figure around the machine. And to prove my point, we challenged ourselves to have like one such use case within our own office for this webinar. So what we did is we took one of these NCD.io sensors. In case you didn't know them, it's a shameless promotion because, well, they really did a great job and they make my life way simpler, while preparing for this webinar. It was really a codeless experience. So we bought these ones, provisioned the gateway, which looks like this. It has, according to the data sheet, kilometers of range. So in theory, you could place one of these little guys in a factory and then have coverage across all of your entire machines. So here, what we did is just we put it in the air conditioning inverter, which rumbles a lot when it's turned on. So it made sense to measure vibration. So let's see how that looks like. So here, it's another one. Here, I have an Ubidots device with all the variables that are being measured by the NCD sensor. Here's another type of view. As you can see, it comes with the 3-axis accelerometer and reports max, min, and the RMS for each axis. If you look at how we placed it, it says that this machine typically vibrates in this, like vertically, like because the rotor would make it vibrate like this. So we would be looking at the X. So if we go to this one, you can see some spikes, which are exactly the times around which it was turned on. Actually, I have it on right now. Probably it's not rotating because the AC already reached the desired temperature, but we can look at the last hour or so, or maybe today, you can see, yeah, you can see when I arrived to the office, maybe, you know, it worked harder in order to get to the desired temperature. And then after there, it's been vibrating around the same type of Gs. This is like a mg, I think it's milli Gs or micro Gs. I think it's milli Gs. So what we need to do from here, this is not a discrete variable. This is a continuous variable, more or less. So we wanted to convert it into something like this, like a 1 or a 0, like, is the machine working or not? And for this, we have something called a synthetic expressions, which allows you to manipulate raw data and convert it into a new variable. So in this case, we have this operator that says, you know, if the variable is above 50, then put a 1, and if not, then put a 0. And with that alone, we were able to create this variable, binary variable. And then on top of that binary variable, we can create a runtime variable, which is what ultimately we'll use as the number to determine whether we need maintenance or not. It's also a synthetic variable where we use accumulated sum. And because this device is sending data every 10 minutes, it will send 6 readings per hour. So we divide it by 6 in order to get the runtime in hours. And there you have it. If I go to my dashboard, we created a dashboard to see these graphs, you know, compared to each other. Let's go back on these 7 days. So here you can see nicely, you know, how there's like a step variable, the binary variable that is 1 when it's turned on, and 0 when not. And the same for the cumulative sum. You can see that it increases while on and remains constant while off. So again, you know, very cool, simple way to tackle one of such use cases. And in order to show how powerful this could get, we would like to share this real example from one of our customers, Genial.io. So it was founded by someone with a lot of experience in IoT at a large technology company. His dream was to build accessible IoT technologies to industrial machines. So he saw this opportunity, the same one that you're seeing, and then he was able to quickly create an entire value offer around some devices that he built using Particle. He was also featured in Particle's blog a while back. And at the end, what they're doing is using these usage-based variables, not only to reduce maintenance costs, but also for billing purposes. So one of his clients builds these little machines to clean car engines, and they charge based on how many hours they're being used. So this usage also helps them, you know, to build their end clients. So here's one of the dashboards that they have with the suggested maintenance date based on the hourly, on the hours that is being used. So very cool use case. Cool. So moving on to our next example. Along the same lines, let's use the same vibration sensor, but in order to know whether something's going on with the machine. Now, if you've been in the manufacturing space for long enough, you will find these devices familiar. These are like vibration analysis devices that are used like on site. They come with different channels. So the one above has 4 channels, for example. And the way they work is like each channel is like a microphone that gets attached to the machine. And then there's a high sampling rate in order to create a frequency response. And then based on the frequencies that the machine is vibrating at, then there's like a diagnosis. So this is similar to calling the doctor. Like if there's a machine that, you think it's not working well enough, you call the doctor, he comes in with all of this expensive equipment and then performs a diagnosis and does a report on site, probably one time per month, or even more spaced. So bringing vibration analysis as an online and ongoing tool would be, of course, very beneficial, because that would be the equivalent of not having to call the doctor thinking that something's wrong, but calling the doctor automatically when you know something's wrong. And to be honest, when I first purchased these NCD devices, I was expecting to do something like this. We'll see in a minute how they solved it, which I think was very clever. But I was hoping to, maybe the hard way to do online analysis, and it's still an option in case you're wondering. If you can get the accelerometer data, do a fast Fourier transformation on using Ubi functions, which is our serverless environment, which packs Python libraries, so you can virtually do any transformation supported by Python, like an FFT. Then after having the spectral response, like you see here, you could pinpoint that the machine is vibrating at this frequency and then report it to Ubidots. Like in this case, it will be this amplitude. The cool thing about this approach is that you can detect more harmonics. So maybe you can report this frequency, you can report this other one and these other peaks at different Ubidots variables. The downside is it's very data intensive. Like if you remember the Nyquist theorem that said you have to sample something at 2 times the frequency that you wish to observe, then we would have to sample at, I don't know, 200 hertz, which would be 200 samples per second. So instead of having, or to get one reading, we would need 200 samples and then, send that to the cloud, and it would just be like bandwidth heavy and processing heavy. So what the NCD guys did, which I think is very practical, is they sample like 500 millisecond intervals. In this case, it's configured to do that sampling every 10 minutes. So, and out of that sampling time, they will send max, min, and the RMS values of the accelerometer. So there's never a frequency transformation. There's always like in the time domain. And instead, what they do is they provide like vibration guidelines saying, okay, if your equipment is vibrating at this much Gs, then, it's a fair condition, rough condition, very rough. Heavy machinery, multiply by this factor and done. So my takeaway here would be, know your problem. Again, going back to the description of this talk, it's a problem-first approach. So if you just want to know if your machine is shaking too much or shaking too strong, just don't go for a spectral analysis. That might be an overkill. Go for something like this. These guys are like $180, clearly more than like an ESP development board. But again, this is industrial grade, long range wireless sensors, and then you're good to go. And to prove that point again, let's look at the Ubidots example. So here we can see when the air conditioning is turned on, this little guy is reporting at 3 different axes, mainly in the X axis, as we saw. This is the main source of information to know whether it's on or off, but it also reports at all the axes, at the other axis. So, in case your machines or your customer knows their machines, so they will likely tell you, okay, this is a rotor, so you can expect X and Y, or it's another type of machine, and then you will know how to interpret whether it's shaking too much or not. This type of anomaly detection, back to the concepts, is, it could be preventive, but also predictive. I would call it either like preventing on steroids or predictive with a very short notice, because it might not tell you like is going to fail in 10 days, but it does tell you like, something's off and you need to service the machine. So anomaly detection using statistics method is also a very practical technique. Similar to that ecosystem slide that we saw, there's a ton of options, but we're sticking to the first one. It's also supported by synthetic variables. So these last two, for example, are already machine learning. The other ones are more like statistical, like traditional statistical analysis. And again, if we look at Ubidots, well, first of all, what is a simple moving average? It's the process of getting like the last readings and computing the average, like the last 10 readings and average. And that way, you do it through all the time series. So what you end up getting is like a smoothed curve, or you can think of it as a sleepy version of the raw data. So why is this useful? Because it goes slower. Whenever your raw data gets an unexpected spike, then the moving average will take more time to keep up. And therefore, if you measure that offset, that delta, you will be able to know whether there's an anomaly or not. To prove the point, we computed the moving average for our vibration sensor in the air conditioning. We can see that oftentimes it works like this. So the moving average is following the original curve. However, when there's a spike, we see a difference of about 20 degrees between the original and the moving average version. So again, very useful to measure. Here you see a great example. So this is what just happened today, where the moving average just takes more time. If we go back, maybe just 7 days. Oh, that was 7 days already. Okay, so if we give it more time, we can see the entire curve. And the way it's done again is using a synthetic variable. There's an expression that allows us to compute the moving average. I can see it here. So it is as simple as compute the moving mean values of a variable. Here I picked 10. If you want to make it more sleepy, you pick a larger number, and then you can use that to again do an alert, which would be something between preventive and predictive. So finally, let's go to the most fun, I think, is machine learning. Again, this is something that was prepared specifically for this talk. So let me share with you that process as a non-data scientist. So first of all, when we think about predictive analysis in general, is the ability to predict an unwanted event. So in the context of predictive maintenance, we have n inputs to a model, and then we want to be able to, given those inputs, predict an outcome. In this case, we want to pose the question, will the unwanted event happen tomorrow? I could pick, within 10 days, within a month. The larger the time window, the more accurate our model could get, because we have more unwanted observations to train the model. So in this case, I picked 1 day. And in the face of the lack of failure observations that we have, because we provide a tool, but we don't necessarily own the data that is going through Ubidots. We asked a few customers, we checked with them if it was able to access some data, and we found that they either had a lot of sensor data around a machine, or machines with a lot of stop and failure data, but not the two combined. Or in the cases that it was combined, it was just not possible to share the data. So what we did, we use the weather model. So imagine an unwanted event, or our downtime, our own version of a downtime would be, will there be bad visibility tomorrow? So we wanted to be able to, given a set of input variables, such as the wind speed, if it's raining or not, if it's sunny or not, the time of the year, the month of the year. Based on all of that, we could say that that contributes to whether having a good visibility or not. So inside Ubidots, this is how it looks. So fortunately, I had this account running for demo purposes, and we had been gathering data about the Boston weather for close to 6 months. So we had a lot of data from a lot of variables like humidity, the visibility, which is what we want to predict, cloudiness, etc. So at the end, what we ended up doing is, again, similar to that binary variable transformation. We created this new variable that says, if there is a visibility below 5,000 meters, then put a 1, and if not, then put a 0. And we did this because the visibility is not a discrete variable. So when I make it like a discrete variable, I can use a classifier algorithm, which is a classifier machine learning algo is like when you have an image, for example, and you want to know if an object is a bike or is a person or it's a pet. Like there's two sets of algorithms that you can use. So one is more like for the continuous domain, and the other one is more for a discrete domain for classification. So we wanted to use a classification algorithm, so which is why we put this variable as simply 1 or 0. So following our example, the process, if you remember this slide, so our idea here was to, how can we get rid of all this noise that we're not supposed to know about because we're not data scientists, and sort of understand that all of that ecosystem is designed to support all of these things, from AI to machine learning, neural networks, deep learning, and understanding the limitations of what we wanted to do, or define it a closer scope, like, for example, time series analysis. We understand that it only moves around 2 things. So it's either purely statistical, like I wouldn't even call it AI, or it has some machine learning component. But even without within the realm of machine learning, you don't need all of these libraries and tools and examples that are out there that are only going to contribute to the noise. So I got very anxious when I had to prepare this, because I was thinking Caroline is going to kill me. I promised I would deliver a talk about machine learning for non-data scientists, and I don't know how I can do this without being a data scientist. But the good news is that it is possible with this big simplification. So at the end, you end up with something like this. Ubidots for data acquisition, which again, it's what we do every day. Even for manual records, there's a widget that allows our customers to input an observation, so not only from devices. And also we have Ubidots plugins, which allows you to pull data from other sources, like the weather, for example. And we're growing that ecosystem. And then, of course, your own devices to measure sensors. And here in the middle, we have Ubi Functions, which is a serverless environment that already has Python pre-installed. So you can run functions in the cloud, saving all the deployment process, which is what could become a headache for those of us who are not software developers. So the process is like this one. So first of all, you have to train your data using historical data. Train your model. There's something new that I found, it's called the feature analysis. Very, very useful. We'll get to that in a minute. And then the prediction is, once you have that model, you get new data, you apply the model, and then you create a prediction. And these are all Ubidots variables. So you grab new data from an Ubidots device, apply the model, and then save the prediction to the same Ubidots device, and you're ready to go. So in the first step, it was as simple as downloading the data. So I literally came here, clicked down, export data, picked, went back to March, and that led me to have an email with a data set of 300,000 observations. So 300,000 was good material to train our model. This is how the CSV file looks like. So it has simply a column per variable. Secondly, okay, this is how you would read it. This, by the way, this training process happens offline, not online. The online part is the prediction. The training process could take place anywhere. It doesn't have to be inside Ubidots. In fact, it's better for you to do it in your own machine because you will have, like your processor and, your Python installation, install your own libraries, make all the experiments you want. And then at the very end, once you have the model, then you upload it to Ubidots. We'll get to that. So secondly, the feature analysis part, I understood it like applying human intelligence to an artificial intelligence process to help the machine, to help the artificial intelligence. One way, if we skip this, we could simply grab all of this historical data and tell the model, I want to predict the target variable based on all the other variables. And then the model will struggle, and then it will come up with a 70% accuracy, for example. The cool thing about the features is the way you embed your own knowledge about the phenomenon to the data set. So for example, imagine you want to do a failure prediction for a process, and then the operator tells you, you know what, Agustin, I don't know what's going on with this freaking machine, but it's always failing on Mondays. And how come on Mondays? I don't know why. Every Monday I wake up and the machine fails. The rest of the days, it doesn't fail. So that's an empirical observation. That's something that the machine will likely not detect because it doesn't see that it's Monday. It just see a timestamp. So it will be hard for the machine to extract the fact that it's a Monday. So what you would do in that case, you would append a new column to your data set that says the day of the week, for example, L, M, W, T, etc. And that way you're helping the model take like a new variable into account to make a prediction. And hopefully that variable will have a lot of weight into how the prediction is done. So in our example, what I did is I added new columns for day, month. Again, it's better to have a month than just a timestamp because the month, we could argue that the visibility, it varies between summer and winter, and therefore the number of the month would make sense for our model to get a better training. The hour of the day also, of course, maybe, at 6 a.m. is different than at 12 p.m. So in that process, I'm helping the model basically. And then also there's all these running measures that are very advised. This is not like human intelligence in place. It's just like a way to help the machine find whether there's like a correlation with the standard deviation of the variable, for example, or with the median. So what you will see in a lot of competitions, like data science competitions, is like they start adding these running measures like crazy. So they end up with a data set with 100 columns or 30 columns instead of the original 10. And that's okay. I mean, columns are free. It won't make your model take way longer. It's just a way to help it. And then, of course, the last ones are very important. If you want to make a prediction, we take this target observation and we shift it so that we can be predicting what's going to happen tomorrow and not what's happening today. This is how simple it was in Python. Like this is the data frame df. So we add the month, a new column called month, new column called day, hour, minutes. I don't have the running measures here, but could also be done similarly in one line. Timestamp, I put it in seconds because it was yelling with milliseconds. I don't know why. And then I drop the columns that I wouldn't be using anymore. So the model training is at the end is like we input this large data set into a function, and then we get these Y observations. What the model does, it tries to find whatever this function is. This is a n-dimensional function to predict the target. It's done like this. Again, everything is built in Python, thankfully. So you take like a training data set with X, which is the X1, X2, X3, like all the columns, and then the Y, which is the target, which is visibility or not visibility. We run, in this case, we picked a random forest algorithm, which was suggested in the tutorials, and well, it was the one that did work. The other ones didn't work that well. And at the end, we can save the model so that we can use it later in Ubidots. So to get an idea of how this runs, I have it here in the terminal. We have the precision score here, which is 79%. And this is how the entire file looks like. It's, it's almost 100 lines, but it's something that, someone with enough Python experience could do with a trial and error experimentation. And if not, we'll be posting this example in our website. So moving on with the presentation, there's a library called Pickle, which is great because it allows you to save a model. So at the end, you end up with your model. Your model is portable. So that's why I said you could do this anywhere in any computer. Once you have certainty that your model works, store it as a bin file. Here I'm plotting the real visibility versus the prediction. So I also have it here as a file. So I downloaded it as a CSV file, and you can see it works pretty well. So here it was the expected one, and here was the prediction. So there are some false positives here, like when you see a blue dot, it means that they were not exactly aligned. And if I filter here, like all the actual predictions, so the moments where the algorithm would have actually said, hey, it's going to be cloudy tomorrow, it was pretty similar. Again, it's 79% accuracy. In this case, I would have been misinformed, saying it would be cloudy tomorrow, but it actually wasn't. But then in most cases, it does work. Again, it's not 100% accurate, but it could be interesting in a lot of cases, especially, you're predicting a machine failure, which again could cost millions of dollars. So moving to the last part of our presentation, the deployment, which is now you want to predict based on new data. So what ends up happening is you receive an aggregation for yesterday, for example, for 24 hours. You apply the model, and then you get a prediction, which is either 1 or 0. This is how simple it looks now deployed already in Ubidots. You get the file from a URL. I'm assuming you hosted it in a URL, and then you run the prediction. And again, how that looks inside Ubi functions. For those of you who might not be familiar with Ubi functions, it's a serverless environment, as I said, which already has Python pre-installed, so you can deploy your own API to do data ingestion, data processing, data analytics, decoders, etc. So in this case, I'm running this function every 60 minutes. So every hour, I'm predicting, what's going to happen within the next. Here's the model deployed. So this is just a binary file. Here we do the data frames. You see the time features that we talked about. We add the month now. We unpack all the inputs and put it into the pandas data frame, and then we simply just run the prediction and store the prediction data in an Ubidots device. So if I go to the actual device, you will find a new variable called prediction. In this case, it's always been 0 because it's running since yesterday. And well, apparently there hasn't been limited visibility days in Boston these couple of days, but we saw the training and we saw that it is successful at predicting the 1 or the 0 when it is likely to happen. So I lost the presentation. There we go. So finally, to wrap up, a few of the use cases that we're observing using one or some of the tool techniques we talked about today. Here's a leading ceramics manufacturing in South America. A lot of machines. They begin approaching IoT from the OE perspective. So they wanted to track productivity, downtime. When they realized they could include critical variables, then it was the perfect mix. Knowing if tracking the downtime and at the same time tracking the variables that affect the machine. These are some of their dashboards. And then here's also a customer in Brazil that's applying the same concepts to excavators. And then in the Ubidots dashboard, it just turns on these units, these alarms on and off based on the maintenance requirements, which has led to 73% reduction in machine stops and a productivity increase of 20%. So a few takeaways. I hope that by now we managed to convince you that predictive maintenance is around the corner, is simpler than most people think. It is not easy, but it's fun to learn. The tools are already out there. It's already supported in everything we do. Start gathering data as soon as possible, or you or your clients, so you can feed your future model. So even if you don't want to do predictive now, you should start as soon as possible, logging failure dates and characteristics in order to feed your future models. Always make a predictive question. It's different if you are answering whether a machine will fail tomorrow or within the next 90 days. And because the machine failure data is scarce, you want to complement with look at historical records to see what you can find, even if it's a lot of years back, and beware of model accuracy. So if a model says it's 70% accurate, but your machine fails only 1% of the time, then you're going to end up with a lot of false positive or false negatives that are going to add noise to the maintenance program. And lastly, the most important one is let's keep predictive maintenance within the domain of IoT engineers without having to hire a software or a data science expert in the process, at least for most of the use cases, which is at the end what we try to advocate from here at Ubidots. So with that, let's open this last 10 minutes for questions or discussion. Thank you very much for being here, all of you.
Wonderful. Thank you so much. As Augustine said, please feel free to unmute yourself and ask questions, or if you're more comfortable, place them in the chat box. I'd be happy to read them aloud for you. Your presentation was so thorough. No one has any questions. What's the best? Oh, go ahead.
I'm so sorry about that. So I do have a question. How much historical data do we need to get a good solution to predict very accurate?
Okay, that's a good one. I still experimented myself, so I don't have a definitive answer. But it's not so much about the historical data, but the proportion between failure data and the normal operation data. You can have 1 million records dating back 3 years back, but if you don't have enough failure observations within that million records, your model is never going to have enough meat to predict the failure. So I think I would say it's more about the proportion. So let's say if you have 1 failure for every 100 observations, then definitely try a model, see the accuracy. If it's not good enough, then try expanding the window. So maybe you don't want to have this, predict if it fails tomorrow, but maybe predict if it fails in 30 days. That way you don't have 1 failure observation. Maybe you have 30 failure observation, and suddenly your ratio becomes 30 to 100. So again, it's an iterative process, but that would be my answer in this case.
That is very helpful. Thank you very much.
Thank you, Rosa, for your question.
Great question. Thank you, Rosa. And we'll leave it open for another minute to see if anybody has any questions. What's the best way if people think of questions later, Augustine, to reach out to you? I know you had the sales email address. Is that the best way?
Yeah, that's one. I can also drop my email address here. We'll be posting this to YouTube, and then in the description, we'll be adding all the links, the relevant links to the examples we just had, including the data set, so that you can test it yourselves at home. And then, of course, leave any questions there if you have it.
Wonderful. All right, I think that's all the questions. As always, wonderful presentation. Thank you so much to Augustine. Thank you, Ubidots. Thanks to everyone for attending.
Thank you. Thank
Thank
all
you
for
very
being
much.
here. Looking forward to do
Thanks.
this on site once we're over with the lockdowns.
There you go.
Here. Okay.
Stay
Thank you all.
safe, everyone. Take care. Thanks.